Hello everyone, welcome to our second video on momentum and impulse. We're looking today at the conservation of momentum, but we're going to be building on what we learned in the previous video on the fact that momentum, P, is equal to the mass multiplied by the velocity of an object, and the impulse is the force times by the time that acts upon an object, which causes that change in momentum, the mv minus mu, i.e. causing a change in velocity on the object itself. Now, conservation of momentum is very similar to the concept of conservation of energy, in that energy that comes into a system must be equal to the energy that comes out of a system. Now, momentum and impulse generally refers to things that are colliding. So when two things collide, they're coming in with different masses and different velocities, which means that this particle will have momentum and this particle will have momentum, and when they collide, there will be some sort of collision and a rebound, and they'll come out with different velocities. But the key thing is that the momentum coming in must be equal to the momentum coming out. So if we think about the two objects coming in, the first object has a mass of m1, and it's got an initial velocity of u1. So m1 u1 is the initial momentum of the first object. Now, if we add that to the momentum of the second object, m2 u2, that gives us momentum of both particles coming into the collision, i.e. the momentum before the collision. Now, that must be equal to the momentum after the collision. So if this is m1 u1, that's the initial velocity of the first particle. The final velocity would be m1 v1. And in the same way, the momentum of the second particle will be m2 v2, and this is our key equation when dealing with the conservation of momentum and the collision of particles. m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. What I'm going to be looking at now are the next few examples in the A-level further maths textbook for momentum and impulse. This is now example number 4. It tells us in example number 4 we have two particles. The first particle is a mass of 2 kilograms, and the second particle is a mass of 3 kilograms. So when I do this, I always draw a diagram. I think it's very, very important to visualize what is going on. You've got a 2 kilogram particle here and a 3 kilogram particle here. It tells us the 2 kilogram particle is moving in at 3 meters per second. So I actually write over here that u is equal to 3 meters per second. The second particle is at rest. So we're going to say over here that u is equal to 0 meters per second. And if you want to, you can actually call this u1 and u2. It's up to you. On the other side, we have the final velocity. Now, it doesn't tell us the final velocity of the 2 kilogram particle. That's what we're trying to work out. So I'm going to call that value v. Now, we don't know actually if this is going to rebound and move in the other direction. What we do know is it's going to hit, and then this particle is going to move forward with a velocity equal to 7/3 meters per second. So I'm kind of assuming that when this collides, it's going to keep going in the same direction. If I work out a value and find that my value of v over here is negative for v1, it means that it just means that it's rebounded and it's moving in the other direction. The other thing I think is important to just put into your diagram, it's not required for this question, is the impulse or the direction of the impulse. Now, because this is coming in and it's hitting the 3 kilograms, it's going to cause an impulse in that direction. It's going to cause that velocity to slow down. And in the same way, this is going to be pushed in that direction due to an impulse from the 2 kilogram block over here. And this is a full diagram for our question. Now, because we said these are vectors, we need to pick a direction to be positive for our velocities. Now, because the motion seems to be going towards the right, we are going to use right as our positive direction. So we're going to have this as, we put our formula down, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2 to the right. And when we substitute in, This is 2 times by 3 plus 3 times by 0 is equal to 2v1 plus 3 times by 7 over 3. That gives us 6 plus 0 is equal to 2v1 plus 3 times 7 over 3 is simply 7. Now, what we notice is that when we rearrange this, we're going to get 2v1 is equal to 6 minus 7 is minus 1, and v1 is equal to minus a half meters per second. And what that means is the velocity has actually, in fact, changed direction. It means that the initial particle has actually rebounded and now is moving in the left-hand direction, i.e. that impulse has caused this to move to the left. So it didn't matter that our v was acting to the right in our diagram. It just means that when we're doing our calculation, we can see that that value has changed. So that's our first example for momentum and impulse and conservation of momentum. We're now going to come to the next example, example number 5, which we can see quite clearly over here. We've got two particles which we are going to annotate. So in this situation, a little bit different. We now have two particles, one which is 2 kilograms and one which is 4 kilograms. But in this case, the particles are actually moving towards each other. The particle that is 2 kilograms is coming in with a speed of 3 meters per second. And the other particle is coming in with a speed of 2 meters per second. Now let's think about this logically for a second. We've got a really heavy particle on the right coming in and hitting a lighter particle on the left. We would probably expect this to probably rebound because it's not going to be able to push that and make it go in the other direction. So we kind of expect this to switch directions, and this may change directions or it may keep going. But what we know is that it tells us that the 2 kilogram particle reverses its direction and travels with a speed of 2 meters per second, and the other particle has a final velocity which we're trying to work out. And I'm just going to assume that it is traveling in this direction. Now, the second part of the question again does ask for impulse, and impulse is just generally in the opposite direction to the initial velocity. So this is moving in this direction, the impulse is going to be in that direction, and over here the impulse is going to be in that direction due to the motion from the other, or the force from the other particle. So once again, we now have the ability to work out our final velocity using our formula of conservation of momentum. But again, we do need to choose a direction as positive. For this, I'm going to choose the direction of right. You don't have to, it is your choice. But we can say m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2 to the right. So we can see over here, the mass for the first particle is 2 times by 3 plus 4 times by minus 2, because that velocity is to the left. This is probably the most common mistake that people make when they're doing questions like this, is they forget that directions are key to these questions. We then have m1 v1, which is 2 again times by minus 2, because this velocity is to the left, plus 4v2. If we now work this out, we end up with 6 minus 8 equals minus 4 plus 4v2. And if we rearrange this, we end up with 4v2 is equal to 2. So once again, v2 in this case is equal to 0.5 meters per second. So once again, just using our formula of conservation of momentum. So we actually can put that into our diagram afterwards if you want to, just to make it easier for the next part. So v2 here is equal to 0.5, and it is still going to the right because v2 is positive. And now we just need to work out the impulse. So our impulse over here is best to choose one of the particles and use the formula mv minus mu. Now in this case, the impulse is to the right, so I'm going to do I to the right on the 4 kilogram block, gives me 4 times by the final velocity, which is a half, minus 4 times by the initial velocity, which is in the opposite direction, so that's minus 2, and that gives us a value of 4 times a half is 2, minus 4 times minus 2 is plus 8, so 10 Newton seconds. So once again, just using those key formulae, the conservation of momentum and the formula for impulse. So that is the topic of conservation of momentum. Effectively, what we've said there is just making sure that you draw a diagram, you show the directions of motion, and you choose a direction to be positive for your conservation of motion, conservation of momentum formulae. Don't forget to also label in your impulses, because when you're working that out later, it makes it easier to visualize which directions are going to be positive. And effectively, I hope that's made sense. If it hasn't, please do let me know. Please leave a comment below or message me directly. Take care. Thank you very much for watching.